Welcome back to Mathematics Lifeline. In today's video, I'd like to discuss the geometric series. Now, this is a type of infinite series that you'll see early in your Calc 2 study of series. This is typically the easiest one that you'll see. But I want to go over and do a few examples of the geometric series today. So we're going to start with the definition, and this is the definition of a geometric series. So it says, let a not equal 0 and r be real numbers. Then in that case, the infinite series from n equals 0 to infinity of a times r to the n is called a geometric series. So that is the formal definition of the geometric series. Now there are a few cases to deal with when we have this. So we look at the absolute value of r, right? And that's this number right here. Whatever that is, if the absolute value is less than 1, then this series will converge, and the convergence sum formula is a over 1 minus r. That's always the case. That is going to be what it converges to every time. Now, if this value of r is greater than or equal to 1, the absolute value of it, if the absolute value of r is greater than or equal to 1, then the sum will diverge because it increases too quickly and it won't converge to anything. So we want to do a few examples of this, finding the sum if it exists, because sometimes the series does not actually converge to any number, right? If the absolute value of r is greater than or equal to 1, then it diverges by definition. So we're going to do a few examples of trying to find the sum of these geometric series. So we're going to start with example 1 right now. Okay, so here we have example number 1. We want to find the sum of this series if it exists. And the series that we have is the infinite sum from n equals 0 to infinity of 1/2 to all to the nth power. Now, one thing I do want to point out is that you may see this written a little bit differently because this is actually the same series as the sum from n equals 0 to infinity of 1 over 2 to the n. This is the same thing because remember, this is also 1 to the n, but 1 to the n power is always just going to be a 1, so we can get rid of it. So a lot of times professors will try to trick you up a little bit by writing it like this, but these series are actually the same. So now we want to discuss if the sum exists. So let's remember the general form of our geometric series. And if you remember, this is the sum from n equals 0 to infinity of a times r to the n. Right? So in this case, all we have is an r to the n. Right? So our r is equal to 1/2 in this case. So we have r equals 1/2. A, we don't really have anything out there. And if we don't have anything out there, that would imply that a is equal to 1. And that's all the information that we need to know because remember, we can figure out the sum if the absolute value of r is less than 1. And the absolute value of 1/2 is equal to 1/2, which of course is less than 1. So we know that we can find the sum of this series. And remember, the general form is going to be a over 1 minus r. Now I know we just went over that, but for this first example, I'm going to show this part because this part is so important. But we have to make sure that the absolute value is less than 1, which it is in this case. So we're going to figure out what the sum is now. So we can say that the sum from n equals 0 to infinity of 1/2 to the n, because the absolute value of r is less than 1, we can say that it's a over 1 minus r. Well, in this case, a was 1 over 1 minus r is going to be 1 minus 1/2. Okay? So now we can figure out this series pretty easily because this is going to be 1 over 1 minus 1/2 is 1/2, and 1 over 1/2 is equal to 2. And that's the answer. That is the sum of this series. So this series will converge, and it converges to 2. And this is just by the definition of the sum of a geometric series. We're able to do this one because, like I said, the absolute value of r is less than 1, and that's all that matters. Once we know that, we know we can just plug straight into this formula, given our a and our r. So we found that the sum of this series is equal to 2. So now we're going to go ahead and move on to example number 2. Okay, so here we have example number 2, and again, we want to find the sum if it exists. So in this case, we have the infinite series from n equals 0 to infinity of 4 times 3 to the n. Now remember that general form is a times r to the n. That's what goes inside the series. So in this case, we can say that a is equal to 4, r is equal to 3. Okay, so you might be tempted to just go ahead and plug immediately into the sum formula, but we need to make sure we check this absolute value of r. So the absolute value of r is equal to the absolute value of 3, which is equal to 3, and 3 is greater than or equal to 1. So because of that, we automatically know that this series diverges. So all we need to show is this right here. And then we can say that the sum from n equals 0 to infinity of 4 times 3 to the n will diverge. And that's all we need to know. And it makes sense, right? Because if we were to plug in increasing values of n, right, we get 4 times 3 to the first plus 4 times 3 squared plus 4 times 3 cubed. That number is just getting bigger and bigger and bigger. And so you can tell that as if we add all of these up, right, we're going to have 4 times 3. That's the first one. Plus 4 times 3 squared. Plus 4 times 3 cubed. You can see all of this. It just keeps increasing. We actually have 4 times 3 to the 0 as well. So that's actually going to be 4 plus all of this. So you can see that this just keeps on increasing. So it makes sense that this series diverges. But we can show that by using the absolute value of r and explaining why it's greater than or equal to 1. But yeah, that's it for example number 2. We're going to go ahead and move on to example number 3. All right, so here we have example number 3, and we want to again find the sum, if it exists, of the series from n equals 0 to infinity of 2 to the n over 3 to the n. Now, when you're looking at this, you may not immediately see why this is a geometric series. But what we're able to do is, like I was talking about in the first example, we can oftentimes rewrite these fractions that we have. So we still have the sum n equals 0 to infinity. Now let's remember this exponent rule. If we have x over y and we raise it to the n power, this is equal to x to the n over y to the n, right? We're able to put that or raise the numerator and denominator to that power because that power is technically being multiplied. So this rule is going to help us out here because here we have 2 to the n over 3 to the n. So working backwards from this case to this case, this is the same as 2/3 to the n, right? So this is exactly what we have here because this is actually the same as this if you use this exponent rule right here. So that's how we can get into the form of a more standard geometric series. The other option would be to write out the terms of this series, but for this video, we're going to write it in the form of the general form of the geometric series. So of course now, we're going to have a equals 1, right? There's nothing out in front of here. And we have r is equal to 2/3, because that is the thing raised to the nth power. Now again, we need to show that the absolute value of 2/3 is going to be equal to 2/3, and that is less than 1. So we know that this series is going to converge, and we need to use the a over 1 minus r formula. So we can say that the sum from n equals 0 to infinity of 2 to the n over 3 to the n, right? This is the general form of the thing. You could write this one as well. This is equal to a over 1 minus r. Well, a was 1, so we have 1 over 1 minus r. Well, we're going to have 1 minus 2/3. So, of course, this is equal to 1 over 1 minus 2/3 is 1/3. And 1 over 1/3 is equal to 3. So this series right here will converge to 3. And all we needed to do was rewrite it in terms of this, right? Because now we have it in the form of a regular geometric series, and we can do the standard practice. And we get the sum is equal to 3. So yeah, that's it for example number 3. We're going to move on to example number 4. Okay, so here we have example number 4. Again, we want to find the sum if it exists, and we have 4 times the series from n equals 0 to infinity of 7 to the n over 8 to the n. Now, if you want to pause and try this one, you're welcome to. We actually are going to do something a little bit different here, but it's pretty standard practice for these. So yeah, we're going to go ahead and get started right now. So we have 4 times this series, and just like the last question, we can actually rewrite what's inside of this series. So this is going to be equal to 4 times the series, n equals 0 to infinity of 7 over 8 to the n. Right? This is standard practice when we have this general form. We want to write it in terms of the exponential. But now you might be thinking, okay, what do we do with this 4? Now, it turns out that, and if you're at this point studying series, you've probably studied integrals. Remember when we do the integral, we'll say if we did 4x. If we wanted to, we're able to pull that 4 outside and just integrate x dx. This is the same thing. We can do the same thing with series. we're able to pull a constant out and we're able to put a constant in as long as it doesn't depend on our variable that's changing. So this is actually the same as the sum from n equals 0 to infinity of 4 times 7/8 to the n. And now you can see that that is in the direct form of our geometric series definition. So we're able to work with this much easier. So it really doesn't matter if you bring the 4 in or not, but you just need to remember it. And I think when we bring the 4 inside of the series, it's more clear that that is equal to a. So we can say that a is equal to 4. We can say r is equal to 7/8 because that is what's being raised to the nth power. Okay, so then again, we need to check the absolute value of r. So remember, the absolute value of r is equal to the absolute value of 7/8, which of course is equal to 7/8, and that is less than 1. So this series will converge, which means we can use the direct rule for the convergence series. So of course that is a over 1 minus r will apply here. So 4, and I'm writing it again in terms of the original question. So we'll have 4 times the series of 7 to the n over 8 to the n is equal to a over 1 minus r. Well, remember, a was 4, so we have 4 over 1 minus 7/8, which this is equal to 4 over 1/8. And when we divide that fraction, we're going to get 4 times 8, which is equal to 32. So that tells us that this series right here will converge to 32. Now, when I was saying that you could leave the 4 out front, we could actually just evaluate this series and then multiply it by 4, right? Because this series, if you evaluate it, will be equal to 8, and 8 times 4 is 32. So you get the same answer. If you want, I feel like this way is a little bit easier because this is the general form, and it involves that 4 without having to multiply it at the end. So you don't have to do an extra step, basically. But yeah, this is it for example number 4. We're going to move on to example number 5. This one's going to be a little bit trickier, but it's still not too bad, and it's still geometric. So we're going to go ahead and do that right now. All right, so here we have example number 5. So this time we have the series from n equals 0 to infinity of 3 to the n plus 1 to the n all over 4 to the n. Now this one is a little bit trickier, and the reason is because this is not as simple as, combining these together, because there's really no way to do it. And a lot of students will make that mistake because this is not the same as, let me write it just as an example, 3 plus 1 over 4 to the n. This is not the same thing, right? Because this would be just 4 over 4 to the n, which is 1 to the n. And that would diverge. But in this case, we actually don't have a divergent series here. So this is not how we would do this. What we do need to notice is that we only have one term in the denominator. So because of that, we can actually split this fraction up. So this is equal to the series from n equals 0 to infinity of 3 to the n over 4 to the n plus 1 to the n over 4 to the n. So you're allowed to do this. This is perfectly allowed. And what we can do from here is, if we have an addition of two terms in a series, we can actually split the series up. So this is the same thing as the sum from n equals 0 to infinity of 3 to the n over 4 to the n plus another sum from n equals 0 to infinity of 1 to the n over 4 to the n. We're allowed to do this. We can split up series just like we could split up integrals, right? We're perfectly allowed to do that. So using this, now we just have two geometric series. So we can work with these individually. So just like the last couple questions, we'll rewrite the first one as the sum from n equals 0 to infinity of 3/4 to the n. And then the same thing with the second one, n equals 0 to infinity. This is just like the first question, where we just have 1 over 4 to the n. And now we can work with these series individually. So for this one, a is equal to 1, and r is equal to 3/4. And for this one, a is also equal to 1, and r is equal to 1/4. And again, we want to check the absolute value of r. So the absolute value of 3/4, of course, is equal to 3/4, which is less than 1. And then again, the same thing here. The absolute value of 1/4 is equal to 1/4, which is less than 1. So both of these series converge, which means that the entire series also converges. So we're going to evaluate these sums individually. So we know that the sum from n equals 0 to infinity of 3/4 to the n, so we're going to have 3/4 to the n, is equal to a over 1 minus r. So it's 1 over 1 minus 3/4, which is going to be 1 over 1/4, which is equal to 4. So that's this one. This one right here converges to 4. So now we want to figure out what this one converges to. So we have the sum from n equals 0 to infinity of 1/4 to the n. This is, again, a is 1, so we're going to have 1 over 1 minus r, which is 1/4, which is going to be 1 over 3/4, which is 4/3. So what that means is that this sum right here, we're going to move right here, this is going to be just 4 plus 4/3, right? Because this one evaluated to 4, this one evaluated to 4/3, so the sum of the series is just the sum of their individual sums. So we're going to have 4 plus 4/3. This is really going to be 12/3 plus 4/3, because 12/3 is 4, and that is equal to 16/3. So that means that this whole sum right here, 3 to the n plus 1 to the n over 4 to the n, will converge to 16/3. So this one is a little bit tricky because if you don't know how to split this up, it's not directly in the form of geometric series. So we do need to do 2 of them, right? And then we're going to evaluate them separately and combine them together. So yeah, that's it for this video. This is kind of the basics for geometric series. One thing I did want to mention before the video ends is if you have a case where, let's say your r was equal to -1/2, the same rule applies, because remember, we take the absolute value of r. So the absolute value of -1/2 is equal to 1/2, and that is less than 1. So of course, if you have a negative, right, the absolute value cancels it out, and you can still do the same rule where r is just going to be a negative number in your final series sum. I realized I didn't do that for any of these videos or any of these problems, so I wanted to point that out before the video ends. But like I said, that's the end of this video. That's it for geometric series. If you have any questions, again, feel free to let me know in the comments. And if you have any suggestions for future videos, again, my comments are open, and I'd be glad to hear what you have to say. But if not, then I will see you in the next video. Thanks for watching.